Find the equivalent capacitance for the combination of the capacitances as shown in the figure, across which the potential difference V is applied. Assume C1 equal to 12 microfarad, C2 equal to 5.3 microfarad, and C3 equal to 4.5 microfarad. So here we have to see the circuit diagram. So in this circuit diagram, we have three capacitors, C1, C2, C3. Capacitors will have different values. One is 12.0 microfarad, and the second one is 5.3 microfarad, and the third one is 4.5 microfarad. So now, if you want to find the total capacitance or equivalent capacitance, first of all, you have to apply the rule for parallel and series. It's depend upon the circuit diagram. So here, if you see the circuit diagram, it clearly shows that C1 and C2 are arranged in parallel. So once you identified C1 and 2 parallel, you have to relate that with C3. So now what I'm going to do, first I'm going to apply the parallel rule for this C1 and C2, and then I'm going to relate that with C3. And I have to draw the diagram also. So that will be easy for our understanding purpose. So first of all, I'm going to apply the parallel rule for this C1 and C2. So here C1 and C2 are in parallel. So what is the rule for parallel? You simply add the capacitors. So here we have only two capacitors, C1 and C2, both are in parallel. So I have to add the values of C1 and C2. So C12 capacitance value, which is equal to C1 plus C2, because this is the rule for parallel. So I have to substitute the value for this C1 and C2. C1 is 12 microfarad plus C2 value is 5.3 microfarad. So when you add, you will get the answer as 70.3 microfarad. So here micro is nothing but 10 to the power of minus 6. Clear? So what is this value? The value is nothing but it's a combination of C1 and C2. Now, if you draw the diagram, so how your diagram will look? Your diagram will looks like this is for C12, and then we have one more, which is C3, and across these two we set a potential V. Clear? Now you can see this C1 and C3 or C1 and 2 and C3 are series. It is in series type, right? So we have to apply the rule for series for this C1 and 2 and C3. So let's write C1 and 2 and C3 are in series. So what is the rule for series? 1 over C equivalent is equal to 1 over C12 plus 1 over C3. So here C equivalent is nothing but for all the three, right? So now we have to apply the rule. So I am going to take LCM. So C12 multiply with C3. In the top, you have C3 plus C12. Now you can see this left hand side. It is 1 over C equivalent. So actually this is a combination of 1, 2, and 3, right? Now, if you want to get the answer of the C equivalent or C total, you have to take the inverse of these equations. If you take the inverse of this equation, your equation will come C equivalent of 1, 2, and 3, which is equal to C12 multiplied with C3 over C3 plus C12. Now I'm going to substitute the value. In the first part, we already have the value of C12 as 17.3 microfarad, and here C3 value we already have in the circuit diagram as 4.5 microfarad. I'm going to substitute that values here. If you substitute that value here, you will get the answer for the total capacitance. So C12 value is 17.3 microfarad. So micro stands for 10 to the power of minus 6. Multiply with C3 4.5 multiply 10 to the power of minus 6 over C3 is 4.5 10 to the power of minus 6 plus C12 is 17.3 multiply 10 to the power of minus 6. Now I'm going to calculate all these. Let's see what is the answer. 17.3 multiply 10 to the power of minus 6 multiply with 4.5 10 to the power of minus 6 divided by 17.3 multiply 10 to the 10 power minus 6 plus 4.5 multiply 10 power minus 6. I got 3.571. So 3.57 multiply 10 power minus 6 farad. So this is the answer for the equivalent capacitance of 1, 2 and 3. It's a combination of all these three. Now if you furthermore modify that diagram, your final diagram will be coming like this. Just see 1, 2, 3 and across these you set the potential. Clear? So we just see the diagram one by one. First our diagram will be like this, and after we took the parallel, our diagram will be modified like this, and after we apply the series rule for this C1 and 2 and C3, once we got the answer, your diagram will look like this. Clear? So between these ends we are just applying the potential. So we are just applying the potential between. So this is a combination of C1 to 3. So we are going to use this answer in the second part of the question. Actually, this is the first part of the question. Now we have a second part. So we have to go back to the second part. So what is given in the second part? The potential difference is applied to the input terminal as 12.5 volts. So in the first part, there is no potential. We are just finding the equivalent capacitance. So if you see the circuit diagram, there is no potential value applied here. But in the second part, we are going to give some potential. So what's the value of the potential? 12.5 volt. Now, if you apply 12.5 volt for this circuit, we are going to find what should be the charge on C1. So here you have to apply the theoretical concept what we studied in the theory class. So what we studied in the theory class, suppose if you have the capacitors in parallel, the potential across the capacitors will be same and the charge stored in each capacitor will be different. So that means if you see this C1 and C2, this C1 and C2 are parallel. So in C1 and C2, your potential, that means the volt across C1 and C2 will be the same value, but the charge stored in C1 and C2 are different. What is the case for the series? When you have the series connection, the potential across each capacitors will be different, but the charge stored in the capacitors are same. So that is the concept we studied in the theory. So now we are going to find what should be the charge stored in C1. And actually, I took the picture from your book because this is a sample problem. And here, if you see the circuit diagram, this is the final answer. For example, you can see we have C1, C2, C3, and you have Q1, Q2, Q3. And also we have V1, V2, V3. So all the answers are already calculated and which is given in the circuit diagram. So what I am going to do, I am going to explain each and every one. And finally, we are going to compare our answer, whether our answer is correct or not with this circuit diagram. Clear? Okay, let's start. So first of all, better I can write what is the rule. What is the rule? If the capacitors are arranged in parallel, what is the rule? Potential across each will be same, but the charge stored in each capacitor will be different. But in case of series connection, it's reverse. Potential across each capacitor will be different, but the charge will be same. So this is the rule we are going to apply here. So now what I'm going to do, I'm going to take the answer what we find in the first part. For example, if you have the total capacitance of these three combination, we must know what is the charge here. So if this is C123 means what is the value of combination Q123, Q123. So what I'm going to do, first I'm going to identify what should be the total charge in the capacitor combination. So I need this answer. So in first step, what I'm going to do, I'm going to find the answer for the total charge. So here what I'm going to do, I'm going to apply the rule for capacitance of the capacitor. In theory we studied the capacitance of the capacitors is given by the rule C, which is equal to Q over V. And if you modify this equation in terms of, because we are going to find the charge, therefore charge which is equal to capacitance multiplied by potential. So that means here we are going to find the charge for the combination C123, and the potential across is exactly 12.5, right? So I'm going to substitute the value. So I need the answer of C123. So I have to take the answer from the first part. What is the answer? 3.57 multiplied 10 power minus 6. So I'm going to substitute the value here. 3.57 multiplied 10 power minus 6, and the potential you applied is 12.5 across all these three, right? So 12.5 volt you applied. So when I just multiply, I got 4.46 multiplied 10 power minus 5. So better, because all the capacitors values are given in terms of micro, better we can rewrite this number in terms of micro. So here we got 4.46 multiplied 10 power minus 5. So I can write this as 44.6 multiplied 10 power minus 6 farad, because this is in terms of micro. Clear? Understand? Okay. Now you can see what we studied. If your connection is in series, the charge will be same, but the potential is different. So we can just go back to your previous question. You can see after you find the combination of C1 and 2, now these two are exactly in series. So now you can see the charge of the combination will be exactly equal. That means the charge in C12 is exactly same like the charge in C123. So charge in C12, because both are exactly parallel. So that means the charge what you have will be exactly same. Once you calculate the final answer, the charge 12 which is equal to charge 123. Am I right? As per the concept what we studied in the theory. So here I have tried. So Q12 which is equal to Q123, which is equal to 44.6 microfarad. Micro stands for 10 to the power of minus 6. Clear? Okay. Now what I'm going to do, let's see what is the potential across the capacitors 1 and 2. So I'm going to find what should be the potential here. Actually in the answer they mentioned the potential across C1 is 2.58 and potential across V2 is 2.58. Why? Because if the capacitors are arranged in parallel, your potential will be same. That's the reason you can see 2.58, 2.58. Right? So we are going to find what should be the potential across V12. So if you want to find the answer for V12, again you have to use the rule of the capacitance of the capacitor, C which is equal to Q over V. Therefore V which is equal to Q over C. So now we are going to find the answer for what is the potential across the capacitors 1 and 2. So if you want to find the potential across 1 and 2, you have to take what is the charge stored in Q1 and 2, and also you have to consider what is the value of C12. So we already have the answer. What is the value of Q12? Q12 is nothing but 44.6 10 to the power of minus 6. And what is the value of C12? C12, you can just go back to the previous part and we already calculate C12. What is the value of C12 here? 17.3, right? So I just take that value. I'm going to substitute that value here. C12 value is 17.3 micro. So 17.3 micro 10 to the power of minus 6. So it will be get cancelled. So when you calculate this, you will get the answer as 2.57 volt. So in the circuit diagram, they mentioned 2.58, right? So better I can see what is the third digit. Maybe the third digit will be more than 5. So 44.6 divided by 17.3. Yes, actually the third digit is 8. So we can write 2.58. So if the potential across V12 is 2.58, means V1 is 2.58 volt and V2 is also 2.58 volt. Why? Because we already studied the rule. What is the rule? If the capacitors are arranged in parallel, the potential across each capacitor will be same. That means you can see the potential across C1 is 2.58 and also the potential across C2 is also 2.58. So it's exactly proved here, because the answer what we have here is 2.58. So if 1, 2 takes the value of 2.58, means V1 and V2 will get the same, because we already know V12 which is equal to V1 which is equal to V2. Clear? So we find the answer for the potential. Now with the help of this, we are just going to find the answer one by one for the rest of the things. So the rest of the things, let's we say we are going to find the answer for the question, because in the question they mention what is the charge stored in capacitor C1. So every time I'm going to deal with the capacitance of the capacitor. What is the formula? Capacitance of the capacitor, which is equal to charge over potential. So now we are going to find what is the value of the charge stored in capacitor C1. So I have to modify this equation, C1 which is equal to Q1 divided by V1. So we are going to find what is the value of this Q1. So therefore Q1 which is equal to C1 multiplied by V1. And C1 value already given in the circuit diagram. So let's see the value of C1, because I forgot. So C1 is 12 microfarad and V1 is 2.5, because we already find the answer here. So I have to use the value here. So C1 12 microfarad. So 12 multiply 10 power minus 6, and the potential V1 V2 same value, so 2.58 volt. So let's see what is the value of Q1. So 2.58 multiply with 12 10 power minus 6. I got the answer here as 3.09 or 096 10 power minus 5. So what I'm going to do, better we write the charge in terms of micro. So how I can write? I can write 30.96 10 to the power of minus 6 coulomb, but we can round it the value of the charge. So how I can write? I can just write these as 31 multiply 10 power minus 6. I just simply rounded the number. So here 31 multiply 10 to the power minus 6 is nothing but 31 microcoulomb. So what is the answer for Q1? So Q1 value is 31 microcoulomb. Let's cross check our answer. What is the value given for Q1? Yes, perfect. Q1 is exactly 31 microcoulomb. Okay, let's try for Q2. So in the circuit diagram, they clearly mention the value of Q2 is 13.7. Again, we will try with the same equation. So this time we have to change. So again, I'm going to deal with the same rule. C2, which is equal to Q2 over V2, and Q2, which is equal to C2 multiplied by V2, and C2 value is already given in the circuit as 5.3 microfarad. So 5.3 10 power minus 6 multiply with V2, because V1 and V2 are same, 2.58. So here I got the answer. So let's receive 5.3 10 power minus 6 multiply with 2.58. Here I got the answer as 1.37. What's the answer? 1.37 multiply 10 power minus 5. Better again, I will round it the number in terms of micro. So I can write 13.7 multiply 10 power minus 6 coulomb. So Q2 is equal to 13.7 microcoulomb. Again, we have to check the answer. Q2 here we got 13.7. So let's check our answer with the circuit, because in the circuit they claim perfect. Our answer exactly matched 13.7. Clear? Okay. Now we have to see for C3, because already I got the answer, because in this question they just need the answer for C1, but I just want to explain what is the charge stored in C1, what is the charge stored in C2, and what should be the charge in C3. I just want to show everything. That's the reason I'm just working here. Clear? So what is the value of C3? So C3 here, they mentioned the value is here, but what should be the potential? The potential is clearly shows 9.92. How we got 9.92? So let's just see. So even everything, if the circuit is connected in series, what's the rule? What's the rule? Let's just go back to the rule. I already wrote it here, right? So if the connection is series, because once you find the parallel with the series, because once you find the capacitance for C12, it will be like this, right? Once you just find the answer, the circuit will be like this. This is for C12, it is with C3, and here you apply the potential of 12.5, right? Now you can see these two are series. If it is series, your potential is different. Am I right? So now what we have to do, we have to find what should be the value of V3. So for getting this V3, what you have to do, the total potential, which is equal to V12 plus V3. So I just apply this rule for this diagram. Which diagram? Just before I draw the diagram, am I right? Because the potential across this C1 and 2 is V12, and the potential across this C3 is V3. So here I compare this with this one with this one. So that means the addition of this V12 and V3 with V3 will be equal it with this 2.5. So we have to substitute the value here to find the answer for V3. So that's the reason I just write the equation like that. So by using this, we are going to find the answer for V3. Therefore, V3, which is equal to V minus V12. So V value is 12.5, but our V12 value, because V12 which is equal to V1, which is equal to V2, which is equal to 2.58. We already found this answer in the previous part, right? So here, in this place of V12, I have to use 2.58. So what should be the answer? 12.5 minus 2.58. I got the answer as 9.92. 9.92 volt for V3. It's exactly proved here. You can see the circuit diagram. Exactly same. Clear? That's it. So we exactly apply the rule and we got everything perfectly. And by using this, you can find the answer for the charge also. Clear? So what is the rule? Because here we used Q123, which is equal to Q12. So when you just use the values here, you'll get the answer, because 44.6 microcoulombs we already found. So the charge across C3 will be 44.6 if you just follow the same method. Clear? Clear, brother? So this is the procedure. Actually, this question is lengthy, so I have to stop up to this. I have to stop the answer up to this. But here, I just want to show what should be the charge in Q2, what should be the charge in C3. All these things we are just using, but just by applying the concept of what we studied in the capacitors in parallel and series. So without that concept, solving this question is a little bit tedious. It's a little bit hard for you. Clear? But it's very easy once you know the formula for capacitance of the capacitor, and once you know how to rearrange this equation, the rest of the things will be easy. But if you did any mistake in between anywhere, the rest of the things will be, everything will be wrong. So you should be very, very careful while you apply the rule, while you calculate everything. Clear? Clear? So better we can write everything together. Here we got C1, C2, C1. In the circuit they mentioned C1 is 12 microfarad, right? 12 microfarad, and the C2 is, what's the value? Maybe 8 microfarad. I think 8 micro, no, not 8 microfarad, 5.3 microfarad. And then C3 is 4.5 microfarad, and V1 is 2.58. V2 is also 2.58, and V3 we found 9.92 volt. And what else? Charge. What is the charge? Q1, Q2 is this one. So I'm going to write the value of Q1 and Q2. Q1, which is equal to 31 microcoulomb, and Q2, which is equal to 13.7 microcoulomb, and then Q3, which is equal to 44.6 microcoulomb. Clear? When you add all these things, for sure your answer will be closer to 100%. And also when you just add these two, you will get the final answer 12.5, because V1 and V2 same. So we just add this with this and you will get the final potential when you apply this. For how much potential you apply? 12.5, right? Yes. Clear? That's it. This is the procedure for solving this type of question. That's it. Thank you.